All right, with the setup from the previous two videos, we are now in position to talk about one of my favorite topics. It's a bit odd, since we really don't have too much experience with spheres that really only have one side to them. It's not to say they're not two-sided spheres, and we'll get to that in a second. But from a previous video, we've been talking about Heegard splittings, specifically of S3. Now, remember, we're looking at S3 as the unit ball in R4, and we can split this up as either the union of two solid balls or the union of two solid tori. But as it turns out, there are only two qualitatively different ways that we can glue these two gold and blue balls together, and that's either with the positive or negative identity maps. But what about the tori? How can we go ahead and glue these two guys together along their surfaces? Well, the identity map could be a choice, but not for S3, not if we want to recover S3. Now, S3, you'll remember, is the 1-point compactification of R3. So, remember that we saw this by separating R3 with a unit sphere into two pieces, and then coring out one of those regions with this vertical tube. So what we're left with inside this sphere is a solid torus, and what's outside is R3 minus a ball with this core. So this makes for seeing R3, almost all of R3, but really R3 hat, as the union of two solid tori. And one of those tori really is just this gold ball with a gold handle attached to it. Now, there's one particular part of this handle that I want you to pay attention to, and it is this little disc here right along what's called a meridian. And this disc, naturally, it has a circle boundary, and we want to look at how this disc interacts with the other solid torus in this representation of R3 hat. Well, as it turns out, this disc is only going to intersect on the boundaries. It's only going to touch this blue solid torus on its boundary. In particular, it's going to touch around this longitude of the solid blue torus. And, well, it goes all the way around this gold bar, this gold cylinder, right? The effective donut hole here. And an interesting point of fact that I want to bring up here that's important to how these gluings are defined. In practice, you don't usually define the entire gluing map. You define where a meridian disk is sent. Now remember, these disks are only going to touch the other side, the other solid torus here, along its boundary. So really, any gluing map is completely determined by where it sends a meridian disk, and in particular, where it sends the boundary of that meridian disk. Right, I'm drawing S3 as the union of these two solid tori, and I only have to specify where that meridian disk is sent on the blue torus, which is only going to be the circle boundary that we see. So, the gold torus is effectively going to plug the hole in the middle of the solid blue torus. And this is exactly what we saw in that picture of R3 hat. And our conclusion is that R3 hat, which is S3, is obtained from gluing these solid two tori not along an identity map, but along the map that takes this meridian to the longitude of the blue torus. So the question now is, what happens if we do use the identity map? What should we get? So let me see about using the second half of this video to try to convince you or motivate how we can see what this space looks like. And what I'm drawing here is just a thick sphere, right? I'm taking a sphere and fattening it up. So each point inside this space is some combination of a location on a sphere, right? So I'm drawing that little red sphere there. So here's where that point lies. And there's also a length along an interval that this point lies. right? And this is effectively defining the thickness, which sphere along the thickness we want to use. And the resulting space is now S2 cross an interval, a closed interval. And let's see, if we glue the outer sphere, S2 cross a point, right, cross 1, to the inner sphere, S2 cross 0, this space now becomes what happens when you glue the two endpoints of that interval together. So you wind up with a circle S1. Now there are two ways that we can glue these outer and inner spheres together. Remember, there's only two qualitatively different maps gluing a sphere to itself. And it's either a positive or a negative identity, so we get either the traditional S2 cross S1 bundle, or we get this twisted S1 bundle if we use the negative identity map. Now, let's go ahead and study this space a little bit, S2 cross S1. The space is home to a solid torus, and this is really just me taking a line segment connecting the inner to the outer sphere and thickening it up into a solid cylinder, which is now a solid torus. But the question now is, what is the rest of the space? What does the rest of this space look like without that gold solid torus? Now, let's go ahead and try to kind of deform that solid torus. We're not really changing it, we're just deforming it a little bit so that it's maybe a little easier to digest what its complement looks like. Now, if I pull it down so that instead of a cylinder I get a cone, then I still have the same space, no problem. Let's pull that cone down so I get essentially a hemiball. It's not quite what it is. You know it's a solid torus. And we still haven't changed anything. So let's continue deforming that solid torus all the way down to the opposite side of the sphere. And what I wind up with is something that looks like what the original blue space was, and now the blue space looks like what the original gold space was. And that blue cylinder we can now see as a solid torus. The conclusion that we draw here is that this space, S2 cross S1, really is just a gluing, a union of two solid tori glued along their common boundary. Now, remember, gluing maps are completely determined by where we send meridian disks. So let's find the meridian disk on the gold cylinder, the gold torus, and follow it through the deformation. So we eventually show that this is almost an entire sphere, except for this tiny little gray disk here at the bottom in the blue solid torus. Come on, gray disk, there you are. And what we've effectively created, or what we've shown, is that one meridian disk, right, the meridian disk of the gold solid torus, is glued exactly to the boundary of the gray meridian disk of the blue solid torus. So what we have just created here is a map between two solid tori that sends the meridian disks to each other. So that means that S2 cross S1 really is just the union of two solid tori along an identity map. Now, here's where the title of the video comes in. The two disks that we just joined together make a sphere. And that sphere does not have an inside or an outside in S1 cross S2 or S2 cross S1. It is a two-sided object, so I mean, it's not like a Mobius strip where you can travel in some direction and eventually wind up backwards. No, this is just a sphere that does not separate the space in which it lives. You can see this by taking a point that would be supposedly outside of that sphere, marching it across the outer boundary, which is glued to the inner boundary, so that you can actually magically arrive at the other side of the sphere. So this really doesn't have an inside or an outside. All right, thanks for watching, everybody. Remember to leave a like, a comment, and consider subscribing. I'll see you in the next video.